Please welcome our next speaker, Eric Eldridge.
Good morning. My name is Eric Eldridge, and I'm a student here at the College of Engineering. And I also work full-time as a contractor for NASA down at Johnson Space Center. So a lot of you here as Houstonians are probably familiar with the International Space Station, or the ISS. What you're probably less familiar with is the robotic arm that is on the exterior of the ISS that accounts for a lot of the operations up there. And that's what I'd like to talk to you about today. We can go over what it is, what it does, what went wrong with it, and how we fixed it. All right, so what it is, essentially the robotic arm mimics the human arm in a lot of ways. It has 3 degrees of freedom at the wrist, it has 3 degrees of freedom at the shoulder, and it has an elbow pitch. Just like a human arm, and also like a human arm, it has a hand at the end. And that's what we call the LEE, and you can see that here. LEE stands for latching end effector. And what that does is it can act as either the base to hold the arm to the station, or it can act as the tip to go out and grab onto things and latch onto them. And so you see that it has 2 LEEs at either end, and we also have 4 cameras, 1 with each LEE, and then 2 near the elbow there. So that's what the arm is. To give you a sense of perspective about it, it's about 58 feet long and about 4,000 pounds. So it is very large. And one of those LEEs, probably about 3 or 4 feet, going to come up to here on me. So it's very big. All right, so what it does, the first thing was it was instrumental in helping with the construction and assembly of the station. So the space shuttle would bring up supplies in its payload bay, and then it would hand off these things to the big robotic arm, and it would take them and move them to where they needed to go around the station. This saved a lot of astronaut crew time, and was also a lot safer to do these things mechanically with the arm than to send the astronauts out to do the construction themselves. The arm also helps to bring in any visiting vehicles. It helps to resupply the station. So companies like SpaceX, Orbital ATK, Japanese high transfer vehicles, they're all bringing supplies up to the station periodically. Food, water, payloads, oxygen, all these things that are essential and critical to keep the station running and keep the astronauts safe are brought up on these vehicles, and they will come up next to the station where the arm will go out, grab them, and then dock them to the station where it can then resupply. So without the arm, if it's inoperable, then that means that this flow of supplies to the station is broken. And that's what makes the arm so mission critical. Whenever there's a problem, we need to fix it immediately if it interrupts this flow of resupplies. Now, I mentioned the cameras earlier. Here's a close-up image of some of the cameras. They're not the best cameras on station, but what they do is, since they are attached to the arm and can move around, they can give us very good views of what it is that we want to see. So when we're trying to investigate different anomalies that go on around the station, maybe an ammonia leak, and we really want to get in and see something, if we can see some flakes of ammonia coming from somewhere, then the arm can get in there and give us the views that we need in order to kind of prescribe what it is that's wrong. And then finally, during EVAs, when we send the astronauts outside, the arm has an attachment that can go on it called a portable foot restraint. And the astronauts put their feet in there, and once their foot is restrained, they can then move around on the end of the arm. And this saves them time and energy, which is crucial during an EVA because expended energy means more oxygen that you're using. And oxygen is one of those limited supplies that cuts the EVA short. So if you're able to keep the crew relaxed, move them around quicker, they're able to get more done. And EVAs are very expensive, very dangerous. So the more you can get done in an EVA, very important, very critical. So that's some of the things that the arm does along the station. So now we want to go back to what went wrong with it. And that's going to bring us back to the LEE, which remember is the hand of the arm. So over here to your left, you see a naked LEE without its thermal covering. And over to the right, you see it all bundled up, protected against the environment of space. And what this thermal covering does is it keeps it protected from radiation, the extreme hots, the extreme colds, and making sure that all the mechanical parts, all of the electrical components are all safe and shielded and able to operate normally. So what went wrong with the Lee? Remember, Lee stands for latching end effector. So that means when it goes out to grab something, it then drives some latches in order to secure that payload object. And the way it does that is the arm provides a current to it. And in order to close those latches, it ramps up the current higher and higher until the latches eventually close on what they're supposed to. But there is an upper limit on how much current the arm can provide. If it gets too high, it becomes a danger to the rest of the arm, and the software will shut it down. And that's what happened in our case. The latches wouldn't drive completely, and so the arm was not able to complete the latching mechanism, and it left it in a degraded state. The arm can't move around. It can move around locally, but it can't grab onto things. It can't work its way around the station. It's kind of like getting a flat tire. You're stuck in one spot, and until that Lee gets fixed, we cannot move around. We cannot grab any visiting vehicles. And so it's become a high priority and something that needs to be fixed as quickly as possible. And that's done via an EVA, where we send astronauts out to put a new Lee on. And so when it's time to do an EVA, that starts at the Neutral Buoyancy Lab. And that's right here in Houston. It's about 10 minutes from Johnson Space Center. And it's a giant swimming pool. It's about 200 feet long, 100 feet wide, and 40 feet deep. And inside of it is a mock-up of the International Space Station. And that's near to scale. And what this pool allows us to do is simulate EVAs in a zero-gravity environment. So we know that on orbit, on the station, the astronauts have no gravity to deal with. And so the pool helps us simulate that in the water. They have a bunch of divers and special suits that all help simulate this environment and help us to create these procedures. And that's where me and my team come in, is going through these test runs at the NBL. We're going through and fine-tuning these procedures so that when they finally go up for the astronauts to execute on orbit, they are perfect, they have been run through, and we're ready for any contingency scenario that might pop up. And so you can see here, we have astronauts on the ground that are trained in the same way as the ones on orbit, and they run through these procedures and will tell us what works, what doesn't, what's easy to do, and what problems they have doing this. Unfortunately, the pool is not a perfect simulation of the zero-gravity environment. There are still some things that you encounter when you move around. You still experience drag. The tools don't work quite the same way, but it's a very good approximation of what it's going to be like on orbit. And so once we've done that, once we've fine-tuned our procedure, then we send it up to the astronauts. And in this case, it was Randy Bresnik and Mark Vandehee, both US astronauts, that went outside in order to do this EVA. And so when they went out, the way the EVA works is, for this procedure, it's going back to the spare tire analogy. It's very much like changing a spare tire. You take the degraded Lee off and put it in the temp stow position. You get the spare Lee that we had stored outside, put it on where the broken Lee was, and then finally take the temporarily stowed Lee and put it back where the spare was originally stowed. And so here you can kind of see some pictures of them going through and doing this EVA. And I'm happy to say that we completed this back in October, and we have a new Lee on the end of the arm. And the arm is back to a fully operational state. The EVA took about 5 to 6 hours in total to get them out of the ISS, moving around and completing the task. And now the arm is back to a fully operational state. So we can go back and get our visiting vehicles. We can go back to doing maintenance around the station, and everything is back to nominal. Thank you.